Welcome to our 11 a.m. press conference. This is about new views of urban heat islands. And just to repeat from earlier, while we welcome people who are not members of the press being here, we ask that only working journalists be the ones to ask questions. And speaking of that, we'll have each of the presenters give their remarks for 5 to 7 minutes and then open it up for questions. We also we're web streaming the press conferences today and this week. Instead of having call-in, which we've had in the past, we have a chat line that reporters who are on the internet can use to ask questions. So we'll also be monitoring the chat, and we will ask questions for them if we find questions on the line from them. So to get started now with our new views of urban heat islands, our speakers in this order of speaking will be Ping Zhang. She's a research scientist with NASA Goddard Space Flight Center and the Earth Resource Technology in Greenbelt, Maryland. Benedicte Dousset, who's a researcher at the Hawaii Institute of Geophysics and Planetology at the University of Hawaii at Manoa. And Cecily Demonck. She's a scientist with the National Center of Meteorological Research in Météo France in France. So we'll go right ahead with Dr. Zhang.
Thanks. Good morning. Before I start, I would like to introduce two key members from our research team, Dr. Martin Hoff and Robert Wolf from NASA Goddard Center. They're sitting in the front row here, and they're willing to help any questions related to this research too. Okay, so why city matters? So can you turn the light a little dark so they can see the video? Thank you. General public should be interested in the urban heat islands. This is because this is where most people live. And by the year of 2030, about 80% of world population will live in urban areas. Urban heat island matters for a lot of things, from the human health to the energy use, like how much heating or air conditioning you need to use to keep your room temperature comfortable. And these two things alone are strong enough to drive worldwide interest. When we build an urban area, we're replacing the naturally vegetated surface or the soil surface with this impervious surface, such as the paving material or the building material. By doing this, we're increasing the temperature in the urban center. So this will generate a temperature difference between the urban center and the surrounding non-urban area. And this is called the urban heat island. The magnitude of urban heat islands varies from city to cities. And from our research, we have been found the several key factors. First, city built in forest area tends to have stronger urban heat islands than cities in other ecology backgrounds. Second, if the background ecology is the same, larger cities have stronger heat islands. And our newest finding is that for cities built in the similar background ecology context and with similar sizes, densely developed aggregate cities produce stronger urban heat islands than sprawling cities with less development density. Scientists and researchers start to study urban heat islands using air temperatures collecting from weather stations or field campaigns. And with the development of satellites, scientists start to take a look at use the land surface temperature to characterize the urban heat. And in our research, we use a variety of satellite data from multiple centers at multiple years, including the ecological background, population data, digital elevation data, impervious surface area. This is satellite measurements shows the intensity of the development and the average summer daytime land surface temperature. So by co-registering all these different data layers together, for the first time, we compare thousands of cities, how the urban heat islands varies and how it's related to the city size and shape and how relate to their locations. And our most recent comparison of sample cities in the Northeast United States gave us an even higher resolution to understand of what causes heat island variance. So our finding number one, the background ecology matters. Because the urbanization will initiate a different heating process between the urban center and the surrounding naturally vegetated surface, so where the city locates matters. Here I show 3 maps of the average summer daytime land surface temperature from 3 different cities built in different ecology contexts or different vegetation types. So on the left is the Baltimore, D.C., built in a forest by ecological context. In the middle is Dallas, built in grassland, and on the right is Las Vegas in the desert. Even though the desert city has the warmest temperature, but in terms of urban heat island, Baltimore and D.C. has a 10 Celsius degree of urban heat island compared to Dallas, it's about 5 to 6 Celsius degree. And for Las Vegas, sometimes the urban center is cooler than the surrounding deserts. So it's a very big heat island, or sometimes it's a heat sink. So background ecology matters. Finding number 2, for cities within the similar ecological backgrounds, we find that the magnitude of urban heat island is log linearly related to the size of the urban. When we're talking about the size, we mean both the population and the physical area of the urban. So here again, I have 2 examples. One is a small town of Lynchburg in Virginia, and one big city in Philadelphia. So both of them are in the temperate forest background, but because Lynchburg is a small town, the heat island is only about 5.5 Celsius degree compared to Philadelphia, it's almost 12. So it's not a surprise. Bigger cities have bigger heat islands. Newest finding, development pattern matters. From our research, we find out there are cities, for instance, Providence and Buffalo, they are building the similar ecological backgrounds. They are building temperate forest. They have similar sizes. For instance, both of them have an urban area about 320 or 50 square kilometers. But the urban heat island of these 2 urban cities are quite different. The urban heat island in Providence is almost twice as that in Buffalo. So we have found out Providence, although this Providence and Buffalo have similar urban area, but Providence has more compact, densely developed center. So more than 70% of the urban area in Providence are highly density urban areas, compared to Buffalo is less than 50%. So it's not a surprise that Providence has a much warmer urban center than Buffalo. At the same time, even both of them are located in forest backgrounds, but the tree cover for the rural area in Providence is much higher than that of the tree cover in Buffalo area. And this results in a much cooler temperature in the surrounding non-urban area of Providence. So Providence got a much warmer urban center and a cooler rural area. So these 2 combined together, it has a much more stronger urban heat islands than Buffalo. So to wrap up this pretty quickly, urban heat islands will varies from cities to cities. And our research using the satellite data compares thousands of cities at continental scale and global scale, and also regional scale, and find out forest cities have stronger urban heat islands than cities in other ecological contexts, such as cities in grassland or deserts. Within the same ecological context, the larger the city, the stronger the urban heat island is. It's a log linear relationship. And the newest finding for cities within the similar ecological context and have similar sizes, densely developed aggregate cities produce stronger urban heat island than sprawling cities. Our next step will be bring modeling efforts to simulate heat, water, energy flux changes with different city types to provide data for urban heat island mitigation. Thank you.
So that's okay. Thank you. So I will talk about the climate change and heat wave in Paris metropolitan area. I'm Benedicte Dousset from the University of Hawaii. And this work was done in collaboration with the Geomère Laboratory in France and an Institute of Veille Sanitaire, which is a public health agency in Paris. So urban heat island, in fact, can also be deadly if you have, for example, an heat wave. And in fact, the climate model predicts for the end of the 21st century an increase in frequency, intensity, and duration of heat wave. And there have been a lot of heat wave recently, and in 2003, in 2006, in 2007, and lately last summer in Moscow. And in this project, satellite imaging were used to monitor the surface temperature of Paris during the 2003 heat wave, which resulted in nearly 5,000 excess deaths. And the image, the satellite image, reveal first contrasted patterns of daytime and nighttime urban heat island and the relationship with the surface characteristic and land use. And the second, that exposure to high temperature during several nights, especially consecutive nights, can double the risk of death for the most vulnerable people. And these people are people over 65 of age, or young infants, or also people with chronic health problems. And also that in terms of mitigating, that a 1% increase of vegetation in fact decrease the temperature by 0.2 C in the afternoon in Paris. So the image we see here, it's in fact a sequence of images. And attends si je trouve le pointer. Okay. Here on this side, we have 6 passes a day with the satellite because we are using 3 satellites. And we have the sequence of image, but each are an average sort of statistics. So each image, in fact, is 8, it's an average of 8 images. Here on this side, you have the night. And here on this side, you have the day. And you see right away the contrast between a centered heat island at night. And during the day, it's still very warm inside. It's like 34 degrees C. But it's even warmer on the outside, on the suburban areas, if you want to compare the scalar difference, otherwise you will not see anything in the image. They are enhanced separately. So on these two, we see very well this contrast. And the reason is that you have nearly no vegetation in the city, so you have no evapotranspiration, while you have that outside in the suburb. And another thing is that you have anthropogenic heat at night. And here, the anthropogenic heat that you have on the industry during the day, you don't have it at night here also. So let's go to the next. And let's go to these images, so night and day. And so it's the average night time, and the heat island here will be about 8 degrees C, which is 15 Fahrenheit. And the highest temperature, in fact, was found south of the river here. And it's also very interesting to note that where there was the most mortality was the highest also. So it's well correlated, highest temperature, highest mortality. And also you can see that these two parks are still cool, and this one is the one represented here. And on the afternoon, you have the heat island mostly on the north, like here, with industrial areas that you see on the last image here. And it's also, you have a lot of warming place according also to the transportation to the places where there is a lot of anthropogenic heat. And what you see in blue are the forests that stay cooler. So it will be cooling in the this part here, for example, the forest here. So what we did is that we did an health impact studies by taking the measurements over, in fact, 482 people, and half of them were people who die, and the other half were people who survive. And we extracted from the series of images, in this case it was 60 satellite images, the temperature at the place where these people were living at the time where the heat wave happened. And so this result, this sort of thermal indicators were run in a logistic model with other multivariable information like the age, like the sex, like the health status of the people, or the housing condition, socio-economical condition, to see the importance of the heat exposure. So what we found is that the exposure to high temperature during several nights can double the risk of death for most vulnerable people, and also that if you raise the temperature of half a degree, but that in the context of the heat wave, you also double the risk for the most vulnerable people. And what's very important to note is that it's the minimum temperature at night, which means the nocturnal temperature. And I don't express that properly. I will say that high minimum, that's count more than the maximum. For example, in 98, a normal summer, the temperature at night were between 8 and 15 degrees. And during the heat wave, they were between 15, I will say, and 20, 25. So that's why the people die, because they were not able to recuperate. When you have the heat stress during the day, and then not able to recuperate for 1 night, 2 nights, 3 nights, in this case it was 9 nights consecutive, then people die. And on this panel here, you have the land surface temperature indicators from the images, the odd ratio, and the odd ratio in fact correspond to the probability of health impact. And it's the minimum. Mean minimal temperature is 2.2, and mean of maximum is less than 1. And if you have 1, it means it's have no impact. If you have under 1, is that the impact is negative, and if you have over 1, the impact is positive. So the impact is very positive for the 7 days, the first 7 days of the heat wave. And if you consider the full timing of the heat wave, in fact, the heat wave was between the 4 and the 13, but it's begun to warm a little before, then it's very significative. So we really have to look at the temperature at night. And another thing, if we want to mitigate this urban heat island and to diminish the impact, a good way to do it is for sure with reducing the albedo, augmenting the albedo of the surface, which means the reflectivity of solar radiation, and by painting the surface, for example, with selective white paint, or choosing concrete which will be very light surfaces. But another way is to use vegetation. And you have a scatter plot here. You have in one, here you have on one side the afternoon temperature. And on the other side here, you have the index of vegetation. And we find that an increase of 1% of vegetation decreased by 0.2 the surface temperature of Paris, which means that if you add, for example, 5% of vegetation, then you decrease of 1 degree. And also that the park that you see on this satellite image have an impact. Even small park like this one you see in green, or a little larger that you see in blue, like or even this one, the Champ de Mars in Paris. And in this case, your temperature can decrease of 2 up to 5 degrees compared with the surrounding environment. So that's about it. Thank you for your attention. Just click. Yeah, sorry. Tu dois cliquer pour retourner sur ton... Tu veux ton... Non, c'est dans l'autre sens. Yeah.
Good morning. Good morning. The findings I'm presenting today about the influence of air conditioning on street temperatures in the city of Paris were obtained through collaborative work between the French Center for Meteorological Research, which I'm part of, a laboratory from the CNAM in Paris, and a company called Climespace, who is a company who initiated this research and who is providing district cooling networks for the city of Paris. So this research was triggered by the last heat wave we had in 2003. I want to start by showing you these two pictures of air temperature maps. These two pictures of air temperature for the region called Île-de-France, with Paris right in the middle. On the left is, these two maps show you the spatial structure of the urban heat island. And on the left, you can see this structure for a standard summer. It's there the summer 2000. And on the right, you can see the same map, but for the heat wave in 2003. So the comparison between these two maps highlights the fact that urban heat island intensity increases during a heat wave. And this conclusion, added to the fact that current climate models predict that a standard summer in France by the 2060s will look like the summer we experienced in 2003, is suggesting that the air conditioning usage is likely to increase massively in the near future. But what do we know exactly about air conditioning? So I will start with some facts and figures. The problem we have in cities about the use of air conditioning systems is that while they are cooling the inside of buildings, they release waste heat in the atmosphere. For example, in Tokyo City, a study showed a 1 to 2 degree increase in air temperatures due to air conditioning usage during weekdays. In France, we lack figures, but we do know that the energy consumption due to air conditioning in August 2003 during the heat wave represented 10% of total electrical consumption. And by 2020, France is expecting a 180 increase in energy consumption due to air conditioning. And this figure is coming from a report commissioned by the European Community in 2003. So we do lack figures about the effect of air conditioning at the scale of the city. And what we wanted to know in this research study was what is the effect of cooling systems on the climate, on urban climate now and tomorrow for the Greater Paris. We wanted to know whether the effects would be different at daytime than at nighttime, whether they would be localized or whether they would be scattered around in the city. And also, we would like to know whether some types of air conditioning systems are worse for the urban climate than others. And here are the findings that came out of this study. So the air conditioning used to meet the cooling needs of Paris buildings during a heat wave, like the one we had in 2003, increases street air temperatures. And this increase is greater at nighttime than daytime, which exacerbates night thermal stress, which could be an additional problem in the light of what Benedicte has just shown us. We also found out that different air conditioning systems have different impacts on outdoor temperatures, and that the proliferation of dry systems showed the greatest increase in the urban heat islands. So in summary, we are faced with a vicious cycle, since temperature increase due to air conditioning will lead to an increasing air cooling demand. And this slide shows you from how much air conditioning increases Paris night temperatures. For 4 air conditioning scenarios, starting with a baseline scenario with no air conditioning, in black, which can refer to a past situation for Paris. Then a real emission scenario, which is accounting for the current air conditioning systems for the coexisting in Paris city. Then another scenario called dry air conditioning, which questions what would happen if all air conditioning systems were releasing dry waste heat into air. And another one, which is the same than the dry one, but with the power of the dry waste heat emission, which would double. And this last one is in pink. And as you can see on this temperature profile, which I'm showing you on this slide, all the scenarios with air conditioning usage are showing an increase compared to the no air conditioning scenario. And this increase in central Paris is about half a degree Celsius compared to the baseline scenario for the real one. 1 degree Celsius for the dry scenario, and 2 degrees Celsius for the dry double scenario in central Paris. Oops, sorry. So this slide is showing you temperature anomaly maps for 3 scenarios with the temperature anomalies for daytime on the top, and on the bottom the same for nighttime. By temperature anomaly, I mean the difference between a scenario with air conditioning usage and a scenario with no air conditioning. And these maps show 2 things. First, that the increase in stream temperature is greater at night. You can easily spot the difference. And that the dry scenarios show the greatest increase in temperatures, with the future one having even more scattered impacts throughout the city. So to obtain these results, we use an integrated modeling of the city. We used the 2003 European heatwave meteorological condition to simulate the atmosphere. And we collated data to build waste heat, air conditioning waste heat emission maps that we incorporated into the description of the surface for the city of Paris, which takes into account other parameters like buildings, anthropogenic fluxes due to road traffic, the vegetation, portions of water, and so on. And we use numerical models to predict exchanges of heat and water between the surface and the atmosphere, and output the temperature anomaly maps I've just shown you. I'd just like to finish with a focus on the air conditioning scenarios we used. For the real scenario, we accounted for the current types of air conditioning systems coexisting in the city of Paris, and we can classify these systems by 3 types of waste heat emission. We accounted for units discharging dry waste heat to air, for units discharging wet waste heat to air, and for units discharging waste heat to the river Seine, which is a technique known as free cooling. Then for the dry scenarios, we questioned what would happen if all air conditioning systems were converted to units discharging dry waste heat with the same power of heat release. And for the future one, we just doubled this power. And the reason for this dry option for medium-term and longer-term scenarios, were that it's very likely that wet cooling towers are going to disappear from the urban landscape due to a health hazard. I think this is called legionellosis or something like that. Yeah, so that's the main point. And I would just like to finish by saying that the double option for this last scenario is probably an underestimate, and anyways, just at the 2020 horizon, and we are very likely to have to face higher impacts in the near future if we account, for example, for the increase in air conditioning for residential use, which we haven't accounted for in this last scenario. Thank you.
Okay, we'll have questions now.
That was really interesting. I have two questions. Let's see. One of them is about the epidemiology on the deaths in Paris. I'm staring at the slide that says heat impact of the 2003 heat wave, and the odds ratio of 2.2. I may have missed something there, but that would be for how much temperature elevation at night that gives you that, because it's obviously, and also as long as I'm asking is what was your control?
The reason, when you said, you talk about the risk factor, which is 2.2, is that?
Yes,
okay.
You list an odds ratio of 2.2.
That's for the night temperature, because what's a night temperature, and at that time the night temperature in Paris was in between 20 and 25. If you take a normal summer, for example, the temperature in Paris will be between 8 and 15, something like that. So it's by raising the minimum, the nocturnal temperature, that you create, in fact, a risk for the people, and mostly for the older people, because this one cannot recuperate of the heat stress they have, they support during the day. You know, they were under a lot of heat stress during the day, because temperature during the days goes up to the 36. So they need the night to recuperate.
So you basically compared the death rates for these 482 people at in 2003 and to a baseline year that was normal?
Yes, no, we did not compare the health in between a normal year. What we know is that the amount of excess deaths we had in 2003, what we look at when we did the comparison was the comparison between the temperature in a normal summer, in this case this was 98, and the temperature in 2003.
Okay. And my other question is about the air conditioning, and that is okay, I understand what is the health risk to what in Arizona are swamp coolers, to the cooling towers, that's having them phased out in Paris, and how does discharge of waste heat to the Seine work?
Sorry, there are two questions, isn't it?
Yeah.
Okay, I'll start with the first one. You meant the health hazard regarding the temperature, or regarding the legionellosis? Sorry.
The wet air conditioners. Why are they being phased out?
They are not currently being phased out, but well, they have been problem of legionellosis, and we have been told that they probably wouldn't be replaced in the near future, and the lifetime of such air conditioners is something like 10 years. So it's probably, they just won't be replaced. I mean, that's the message at the moment. This is not my part of work.
How
really.
does discharge to the Seine work? Is it just pumping water through a building?
It's just, this again is more the speciality of my colleagues of the CNAM. Basically, when you reject waste heat directly to the air, it's just the entire heat is rejected to air. When you reject something with a wet, the wet waste heat is basically used to vaporize water, and so it's only a portion. I think it's just 5% of the total power, which is actually dry rejected to the air. So it's actually less than the total power.
Hi, so James Dacey, Physics World. I was just wondering, so after the heat wave of 2003, have the authorities in Paris, have they changed the landscape at all? Have they, you can do things like painting buildings white to try and cool down the city. I mean, have they responded in any way?
Well, there have been research projects about that. The main constraint with Paris is that we cannot do very much about the historical center, because they are building, there are regulations, and we cannot basically touch these wonderful Haussmannian buildings. So the research is more focused on what could we do somewhere else than in the center of Paris, for example, in the surroundings. And we were part, not myself, but my team has been part of a project which is called the Grand Paris, which is a bit like the big bet. What can we bet about the future? And we did a modeling study by using wet paint for roof and road surfaces, but in the surroundings of Paris, and increasing also the proportion of woods around Paris, and it showed an effect in central Paris, which was a decrease of about 2 to 3 degrees Celsius. You want to add something else?
I will add that in terms of the health, they completely changed their alert system, so it was improved.
My question is for Madame Dousset. You mentioned that with 1% more vegetation in Paris, you could lower the temperature by 0.2 degrees Celsius?
No, oui, c'est ça, by 0.2, yes.
Yes?
Yes,
okay. I have a couple of questions about that. The first one is that in normal circumstances or during a heat wave. And the second one is 1% more vegetation, 1% of what? Of the trees in the city center where there are a few, or do you include the suburbs where there are many, or even the forests?
I did not hear. Sorry, can you repeat that?
So 1% of more vegetation, but 1% of what? What is the base from which you calculate that?
In this case, it's vegetation in general, because of the data we take. We are not able to see if it's forest or if it's park. It's in general. In case of the Ile-de-France, we have some forest around Paris, and we have mainly parks and little and tiny parks also disseminated inside Paris. So I'm sorry, but I cannot say if it's more trees or lawn, but it's vegetation in general in this case. 1% of index of vegetation. If you take the total of vegetation, and if you put that in percent, if you add 1% more than one exists, that will happen.
So that is the index of vegetation locally, not over Paris, but locally. So for instance, to make this understandable for my readers, I would like to know if I have a street without trees, and I would plant, say, one tree every 20 meters in the whole street. What would I do to the temperature in the street?
Complicated to give you a number right now, but it will certainly have a positive effect.
Of course,
but I cannot, at this scale, I cannot say,
I would like to add some comments about that. So researchers tend to use remotely sensed vegetation index called the normalized difference in vegetation index to represent, the density of the vegetation. So that index will vary from 0 to 1. Normally, the higher that index means, you got more densely vegetation. And the relationship between this temperature difference and this vegetation index difference is not unique. Let's see, you can see from her research, you got this relationship about for 1% decrease, you got a 0.2 Celsius degree increase in the urban heat island. When we did similar research using thousands of cities at a global scale, and our found that at a global scale, this relationship is about 0.1. So it's much lesser than the case in Paris. But just let you know, in general, the more vegetation you have, the cooler temperature you will have.
If I can just very quickly add on something. I think your question comes just a bit too early, because there are ongoing researches about different types of vegetation. on the effects on temperatures. And we are involved in a few projects where we're going to study the different impact from a green wall, a green roof, street trees, and things like that. And they don't have the same effect, because some just have provide evaporative cooling, but some, like trees, have also shading effects and things like that. So I think if you wait for another couple of years, you may have a clearer answers and with figures as well.
Dr. Zhang, Jonathan Amos from BBC. Can I just clarify the different mechanisms at work here? We say that if we add vegetation, we cool, and yet your observation here is that cities and forested areas have strong heat islands. So I'm not quite sure what the different drivers, the different mechanisms are here.
That's a good question. Well, I would see that at a global scale, we did 1,000 of cities average. So global scale, not matter how big the city is, for all the urban areas bigger than 10 square kilometer squares, the average UHI, or the urban heat island in forest cities, is about 3 Celsius degree. Compared to cities built in grasslands, it's only about 1.5 Celsius degree. As in average cities like deserts, is 0. It's like nothing. So, but this number will vary when you check, for instance, when you check the cities from different regions and with different sizes. For instance, from our research, if we only focus on the big cities in the United States, that number will change a lot. For the top populated cities in the United States, the average urban heat islands in forest cities is about 8 Celsius degree. Compared to the grassland cities, is about 5 to 6. And again, to desert cities, is about -1 to 1 or 2 Celsius degree. I hope this answers the question. You will have some.
It's a relative.
Yeah, the urban heat island is a relative number. It's always compared to the surrounding non-rural area. Am I answer your question?
Well,
I can answer also to that. Is that what we call heat island is a differential between the outside the city and the inside the city. If you have vegetation outside, then you have evapotranspiration, and the city is mineral, so the city will be warm. If you compare, for example, if you take a city in the desert or around Phoenix or places like that, then the city will be mineral, the outside will be dry, there will be very little difference. Now take a city with a forest outside. Forest will be cool, city will be warm, then you will have a larger difference.
Harvey Leifert, freelance. I understand the concept of the heat island and the basic material you've been presenting, but talking about the deaths that occurred in Paris in 2003, the temperatures achieved in Paris that year were quite normal in Washington every year. And people are not dying of heat in Washington, or hardly any. But, so my question is, if you simply had more air conditioning in Paris, wouldn't this be an easier solution than planting millions of trees, which just doesn't seem practical?
One sentence. Only for people who have air conditioning, not for the neighbors who haven't got any.
Of course, you would have to have more. I mean, Europeans have always been sort of been amused at how Americans rely on air conditioning, and it seems now that you may have to, in fact, invest in this. If you have a gradual increase in temperature between now and 2060, I don't think in 2060 you'll have the number of deaths in that year that you had in 2003.
There's two things. That first, Paris was not equipped well for heat wave like it's happened. It was a surprise. And it was in the months of August where I would say a lot of people are taking their vacation, their holidays. So the structure was weak to face the event. And there is little air conditioning in Paris. And also, yes, If you compare with Washington, you have a lot of green. It's a little like cities like LA, or when you have the green inside the city, you know, if you look at, for example, even Bethesda, it's full of vegetation. Maybe just the downtown have less vegetation, but on the other hand, downtown is more administrative. Not a lot of people live there. And the structure of Paris is very different. It's very dense, and no vegetation nearly in the street, or very little, a few trees, and some parks that are scattered. So the condition of people living in Washington, there is also more wind circulating. It's not as dense. So I think at night you have more cooling than you have in Paris. And in fact, I have image. I cannot show that, but I have image of I would say heat wave event, not heat wave. I would say extreme heat in Washington, and that show that very well. Yes, I can show you that after if you want. Sorry.
Hi, I'm Mason Inman, a freelancer. This is a question for Cecile. So it says a standard summer in France by the 2060s will look like summer experienced in 2003, but that's for the IPCC A2 scenario. How is it different for other scenarios with lower emissions or even higher emissions?
Well, I've got a colleague here who has just presented something about, Annelise Bolin, who's just presented something about future heat waves. And by the end of the century, it is forecasted anyway, even with the A1B scenario, with lower emissions, that the intensity, the number, and the duration of heat waves are anyway going to increase. I don't remember exactly. I think the increase in number of heat waves are two heat waves per year by the end of the century. At the end of the century, yes.
And in 50 years' time, if we cut emissions a lot, is there much chance of cutting the rate of heat waves?
Sorry, can you say that again?
If we, can we avoid this if we cut emissions a lot?
Oh, this is. I think it's out of my subject, and I even being optimistic, I'm not sure that we're going to cut down enough to actually reduce all these effects.
Davide Castelvecchi from Scientific American. I have two questions for Dr. Zhang. One is, it seems really the findings about Las Vegas seem really counterintuitive, and how is it possible that you have that Las Vegas is cooler than the surrounding desert? And I know that there's a lot of fountains there, but I don't know if that's enough. And the other one is you compared cities which have comparable surface area but different rates of development. Some of them are more developed than others. Do they have similar populations, or does the rate of development also correlate with population size?
For the first question, is that you need to remember that this urban heat island is always a relative number, so you always compare to the surrounding areas, and for deserts, because the heating parameters of this sands and everything tends to have this very high surface temperature and also air temperature, and when we building the urban areas, and for Las Vegas, actually people tends to have some trees or parks or lawns or grass, among your house or in the street, and that's why this temperature in this Las Vegas is actually cooler, sometimes cooler than in deserts, because there's basically not too much vegetation in the deserts area. And I hope this answers your first question. The second one. Yes, when we choose our case studies in Providence and Buffalo, yes, these two cities have similar populations.
Okay, we have time for one more question.
Allison Hawks, also freelance. Just in terms of the sprawling cities versus the more densely populated cities, Is the difference there just that the sprawling cities tend to have more vegetation? Is it, again, an issue of vegetation?
Yeah, I would say, yeah, it's also vegetation.
Okay, thank you very much. We appreciate everyone coming and our presenters giving their, talking about their findings. Our next press event will be at 2 o'clock. We'll have John Holdren here for half an hour to take questions from reporters, and after that, Jane Lubchenco. John Holdren is the director of the Office of Science and Technology Policy. He's giving a talk at 12:30 to 1:30 over in the Marriott, and then he'll be over here at 2. And then Jane Lubchenco, who's the NOAA administrator, will be here at 2:30 for half an hour to take questions from the press as well.